I am Richard Clafter, and this is Eric Swanson. This is our first time talking here at DEF CON. Looking forward to it. In fact, this is our first time being at DEF CON. It's been tons of fun. Anyway, today we're going to be talking to you about checking your fingerprints. Specifically, we're going to be talking to you about checking your GPG fingerprints. So we're going to do a little bit of background just to get everyone up to speed. GPG is an open source alternative to PGP. It's a general encryption and signing tool. And it's a very important anti-surveillance tool. That is, it's used for both sending secure messages between individuals, corporations, et cetera, and signing packages and messages so that you get the message. It's from who you think it is. There are lots of good resources online. This is not going to teach you how to use GPG. There are a few important things to understand. First off, GPG is used everywhere. It's the most widely used email encryption package, and it's used extensively for software package verification, which is kind of some of the stuff we're going to be talking about. And there's lots of people that use GPG other than privacy-conscious crypto nerds like me and a lot of you probably, including journalists, lawyers, activists, et cetera. And I'd like to mention that these people don't write the software. They don't necessarily understand how to use this, but I think it's important that they can use this competently and safely because their jobs and often their lives depend on it. So in order to exchange a secret message, you must get the receiver's key. And this is normally done via the GPG key servers. And to specify a unique key on the GPG key servers, you specify either a fingerprint, 32-bit ID, or a 64-bit ID. You receive the key, and once you receive the key, you verify that it's the key you think it is. That is, there are two ways often doing this. One is to manually check the fingerprint character by character, and the other way is to use the Web of Trust. More on that later. And the big problem with this essentially is that mistakes are fatal. If you trust a key that you shouldn't be trusting, and there's no recourse, you've lost, which makes this key exchange part very, very hard.
So the Web of Trust is the most commonly specified way to do key exchange with GPG, and it's one of GPG's big innovations. Again, the whole point of this authentication is to verify that the key you got is from who you think it's from. So it's from somebody with the correct ID and everything else. And the Web of Trust is the most popular decentralized method for key exchange. People have built a lot of other things on top of it, and it's very cool. But it's also very hard to use. In order to get into the Web of Trust, you have to find somebody that you trust, verify their ID, and verify that they will check other people's IDs. And then you can only trust them so far as you verify that they perform the same steps and so on. And this means that a lot of those other users the lawyers and activists and the like, don't join the Web of Trust and instead rely on less sophisticated mechanisms. Also, GPG as a tool has a somewhat complicated interface. You have to use some arcane command line options or the interactive mode or a couple of other ways to verify that you trust a key. And it has lots of complicated questions that, again, can scare off a less sophisticated user. And even Debian, which is well known for being a pretty secure operating system, tells users to ignore the message, "No ultimately trusted keys found," because that's part of the Web of Trust and they didn't want to get into it. And we've all seen what happens when you tell users to ignore warning messages. So we promised a demo in this talk, and here's our demo. We're going to install Puppet and its signature from our mirror. And since we don't trust our mirror, we're going to verify the signature with GPG as the documentation tells you to. So first, we need to get the two binaries. And this is from our secretly evil mirror at mirror.evil32.com. Now we'll follow the documentation. They tell us to request the key by the 32-bit ID. And you'll see two keys imported. Now we'll verify the fingerprint following the documentation. And you can see in here, all right, let's see, 47B3. Let's see how we can make this a little bigger. 47B3, 47B3, 20EB, 20EB, 4C7C, 37A5, 5A, and so on. Now, of course, you should verify the full fingerprint, but in the interest of time, I won't go through it. And then finally, we'll verify the source tarball that we downloaded using the signature we downloaded against that key that we just fetched from the key server. And you see it says good signature. Now, there is this warning here saying it's not certified, but both Puppet and Debian have told us, oh, don't worry about that warning, it's no big deal. So it looks good, we can go ahead and install it. And we just got owned. Now it turns out that when we fetched the keys, we received 2 different keys. You can see them both here. Here's one key's fingerprint, and then here's the second key's fingerprint. This was the evil key. Unless you were paying particular attention, you might not have noticed that there was a second key, or maybe you would have thought, oh, well, there's 2, no big deal, this one matches. So the truth is that humans are broken, not the encryption. Humans make mistakes. We're bad at comparing long strings, and we're particularly bad at noticing differences in output that we see often. So as you can see below, if you request the key with a short ID of 10000001 from the pgp.mit.edu key server, you will receive 2 keys back, one for John Doe and one for Jane Doe. But if you import keys frequently, you might not notice that you got 2 keys, and you might not notice that they were for 2 different people. But they're both in your key ring now. And GPG doesn't say anything to warn about this. It returns the same status code. Everything looks normal. And slightly more worryingly, GPG doesn't even verify that the received key matches for the one you asked. So if you ask for the fingerprint, the full fingerprint, but there's, for example, a man-in-the-middle break. So in this case, we have a server impersonating pgp.mit.edu, which returns back the 0 bad beef key. Clearly, that doesn't match the fingerprint we asked for, but again, GPG gives no warning, and this key is in your key ring. Since GPG doesn't verify anything, the key servers can tell you to import anything they want, and since the key servers don't use transport-level security or anything else like that, they're vulnerable to man-in-the-middle attacks. So for a practical exploitation of that, this line comes from Docker's install script. If you use apt key advanced and you give it the received keys with a full fingerprint, but again with a man-in-the-middle break, you'll see that we fetched the 0 bad beef key, and now that's in your apt key ring. And again, this comes from the script at git.docker.io. So there's a few caveats with this. None of these examples on their own will result in a practical break. Both Puppet and Docker will give you their binaries over SSL most of the time. In this case, they're merely trying to check that GPG signed box. They're using TLS to give them the real security. But TLS relies on certificate authorities, and we all know, VeriSign, DigiCert, certificate authorities are not to be trusted. We love GPG, and we want to have a good decentralized option that can replace certificate authorities. But when it's used like it was used in these examples, it adds nothing to the security. If the HTTPS weren't there, it wouldn't be secure.
Okay, so for finding these fingerprint collisions and some of this fun stuff, we wrote a tool. It's called Scallion. And the general way, very high-level view of how Scallion works is it generates 500 million GPG keys a second. It does this on the GPU. And for each key, it checks for partial fingerprint collisions. Now, Scallion runs on any modern GPU. Old Bitcoin hardware is Prime on OpenCL. And you can grab source and such at evil32.com. A little bit more detail. Essentially, the first step in generating these GPG keys is we generate an RSA key with libopenssl. We send the key to the GPU, and we increase the public key's exponent, hash the key, and steps 3 and 4, we do 500 million times a second. If there's a partial collision, we send it back to the CPU, and bam, you have a brand new GPG key with a partial fingerprint collision. So what are the implications of this? So first off, 32-bit key IDs are ridiculously broken. They've been broken for some time. You can do this on a CPU, but on our GPU with our software, it takes a few seconds to do this. To demonstrate how easy this is to do, we cloned the entire Web of Trust strong set, which is about 50,000 keys, in one day on a 4-year-old Bitcoin miner. You can check out our clone key server at keyserver.evil32.com. Okay, so another way that you could specify how to receive a key from GPG's key servers was 64-bit key ID. So this is like the obvious path to go for to make this more secure, use more bits, right? And this one's already there, you can already use it. So at the moment, finding a specific key with 64-bit key ID is not very practical. However, let's say we wanted to find one of 100 keys. We have a list of 100 different software packages, and we just want to find a collision. Given 20 GPUs, looking for 100 keys, it would take approximately 107 days to pull this off. So, like, this is strong fairly at the moment, like, not practically broken, but in the long run, this isn't going to work it.
So This leads to two big classes of vulnerabilities. First of all, if the attacker owns the network, they can exploit the fact that GPG performs no verification to send arbitrary keys back to you in response to receive keys. And this one might seem a bit obvious, but they can tamper with the fingerprints and documentation that's served over an insecure channel. I've seen a lot of cases where documentation for what fingerprint to use is just over HTTP, which doesn't add very much in level of security. And if the network is secure, then things are a little bit better. The attacker can still exploit 32-bit key collisions to return multiple keys with the same ID, and as you saw, the output looks very similar when this happens. And they can also upload arbitrary data to the key server. So keeping with the slight Bitcoin theme here, I looked at Satoshi Nakamoto's key, and his key was created in 2008, and there are two signatures on his key that start out, one in 1995 by Dade Murphy from Hackers, and one in 2001 by the time traveler from Usenet, John Titer. So neither of these seems particularly legitimate, but the key server is happy to show them to you, and GPG is happy to import them when you request the key. So takeaway. If there's 3 rules to follow, these will keep you pretty safe with GPG. First of all, always verify your fingerprints by hand. Follow the full fingerprint and make sure you get it from a trusted source. Or use the web of trust and understand what the implications of that are. Second of all, don't trust the key server. In particular, even if you request a full fingerprint, that might not be what you get back if the network is not secure. And finally, don't use 32-bit key IDs anywhere. Don't put them on your blog, don't input them into GPG, certainly don't put them into software documentation. For the people who need to fix the problem, GPG's UI is broken in a couple ways. First of all, it shouldn't accept 32-bit key IDs anymore, and it shouldn't display them by default. There is a format option you can put in your config that will make it show 64-bit IDs by default, but it will still accept 32-bit IDs, and it will still show you keys that collide. Second of all, if there are key collisions, that seems pretty unlikely. GPG should give you a warning if you ask for a key, especially by fingerprint or by ID, and get a collision.
Okay, so we have if you want to know more about the project, more GPG UI hacks, get access to the key server, source code, etc., you can check out our site at evil32.com. There's additional material we didn't cover here today on this, so it's definitely worth checking out. And I think we have a few minutes left, don't we? I think we do. Does anyone have any questions or anything?
Have you looked to patch GPG to eventually, I guess, keep that desktop?
We have not looked into it yet, but that's like kind of on my to-do list. We were doing the presentation, but that seems like blatantly obvious. It shouldn't break anything. Like should be pretty easy to do, you'd think.
So one challenge with that is that you can request key by UID, so say by last name or by email, and it will perform a search on the key server and return those keys. So it is somewhat reasonable that you could want to import every key with a certain email domain, for example, and use that. But that would kind of rely on you having a trusted key server, maybe in an organizational setting or something like that. So that would be a little bit of a caveat, but I think that would be a good first step for GPG to do. Anyone else? Yep.
What kind of implications does it have for email security, like email?
So the question was, what kind of implications does this have for email security? Most notably, it's problems in key exchange. If you can safely get the key from the counterparty, then there's no implications for this. GPG as a tool is very solid. The problems are in the user interface and the social engineering exploits this opens. Does that answer your question? Okay. Okay, if there's no one else, we can talk a little bit about the tool we created, if anyone finds that interesting. All right.
Sweet. Go ahead.
No, you go.
All right. Okay, so Scallion is actually, started writing it a couple months ago, more than a couple months ago, and it's actually originally intended to generate addresses for Tor hidden services, which essentially consists of generating an RSA key and doing a SHA-1 hash. In order to generate enough RSA keys on the GPU, what we do is we increase the modulus, right?
Public exponent.
Public exponent, I always screw that one up. And that is, we don't actually have to regenerate the key, we just change the exponent, take the SHA hash, and we can check it.
So that was pretty much the key insight, was that we could take the public so an RSA key consists of a public modulus and a public exponent, and then the private secret components as well, which are the 2 factors of the modulus and also the private exponent. And so the sort of insight was that we could take this public modulus, public exponent that were generated fairly slowly on the CPU, And then, again, this kind of came from Bitcoin as well. We could increment that exponent as if it were a nonce and look for other keys. And then we just take the SHA on the GPU. We wrote some pretty clever code to give general regex, or give some limited regular expression support. So you could match against regular expression patterns on the GPU efficiently. And this is what let us ask for all of the keys in the strong set in such a short amount of time. And then there's a couple of other things that are particular to GPG that, for example, the creation time is also part of the hashed packet. But in general, this will let you make, least interestingly, a vanity GPG key. So you saw the 0 bad beef key. And also any sort of collisions you'd like. So let's say maybe your 1 and 2 4-bit DSA key is looking a little bit long in the tooth. Maybe you'll want to make another one with the same key ID. So you can make an RSA key 4096-bit using the same thing. And then the Tor implications are pretty cool too, in that Tor uses, they kind of cheat on the key exchange problem by making the users type in the first 80 bits of the hash of the key in the address. So the onion address is just the first 80 bits of the SHA-1 hash of the public key of the hidden service. And this tool lets you generate various vanity SHA-1 hashes. So for example, the Silk Road's old hash, which was Silk Road, I think 8 or something like that. They used another tool and did it on the CPU, but we generated the same hash in like 2 minutes on the GPU. All right. If there's nothing else, we're going to be across the hall in the Crypto and Privacy Village. They have a key signing party that starts at 4, so we'll be over there if anyone has any questions. Thanks for watching.